Hi, my name is Dennis Angel. I'm an XRPL core developer at XRP Labs, and today we're going to be talking about the XRP Ledger. So what is the XRP Ledger? The XRP Ledger is a cryptographically secure, immutable record of the complete state of the XRP Ledger network at a specific point in time. Its core characteristics are that it's immutable, so once validated, ledger data cannot be altered. It's sequential. Each ledger builds upon the previous one. It's complete, so each ledger contains the entire network state. It's also distributed and replicated across all network participants. The ledger chain concept is a sequential progression. So we have a genesis ledger, ledger 1, ledger 2, ledger 3, and then the current ledger, which is the ledger we are on. This means that it's cryptographically linked. Each ledger references its predecessor. It's a monotonic sequence. Ledger numbers always increase. Temporal ordering represents the passage of time in the network, and state evolution means that each ledger represents a state transition. So why this sequential design? It ensures deterministic ordering of events. It prevents double spending and race conditions. It also enables efficient synchronization between nodes and provides a clear audit trail for all network activity. So now let's look at the ledger versus transaction paradigm. Traditional database approach modifies records in place. Current state overwrites the previous state, and history may be lost or archived separately. The XRP Ledger's approach is an immutable state snapshots, has complete history preserved, and state changes through new ledger creation, while transactions are the mechanism of which ledgers are the result. The benefit of ledger-centric design is the auditability, where complete ledger history is always available, consistency, where all nodes have identical view of the network state, recovery, where we can rebuild the state from any point in history, and trust, cryptographic proof of all state changes. Next, we'll look at the hierarchical data organization. It's a three-tier architecture. First is the ledger header. This contains the ledger sequence number, the parent ledger hash, transaction root hash, account state root hash, and the timestamp and close time. The second tier is transaction set. All transactions are included in this ledger, organized in canonical order, and each transaction with its metadata and results. Finally, we have the account state tree, which is a complete snapshot of all account states, including all ledger entries, accounts, offers, and trust lines. And this is organized in a Merkle tree for efficient verification. Next, we have data integrity mechanisms. First is cryptographic hashing. We use SHA-256 to ensure data integrity, where all modification changes the hash. This provides a unique fingerprint for each ledger. We also use digital signatures, so validator signatures on ledger proposals, transaction signatures from account holders, which prevents unauthorized modifications. Third, we have consensus validation. So multiple validators must agree on the ledger content. This solves the Byzantine fault tolerance and prevents single points of failure. And finally, we have chain validation. So each ledger must reference the valid predecessor. Breaks in the chain are immediately detectable, which ensures temporal consistency. Next, we'll go over the ledger lifecycle. There are 4 phases of its creation. So first, we have transaction collection, where we gather pending transactions from the network. We apply these transactions based on queue ordering rules, and we filter invalid or expired transactions. Next, we assemble the ledger. We apply these transactions to the previous ledger state. We calculate new account balances and states, and then we generate transaction results and metadata. Third, we move to the consensus process, where validators propose their assembled ledger. The network reaches agreement on a canonical version, and disputed elements are resolved through voting. Finally, we have validation and finalization, where the final ledger is cryptographically sealed, distributed to all network participants, and becomes the immutable part of the chain. Next, we'll talk about transaction ordering and determinism. Why determinism ordering matters. All nodes must process transactions identically in order to reach the same final state. Some of the ordering principles: canonical sorting, so transactions are sorted by cryptographic hash; fee priority, where higher fee transactions are processed first within the ledger; account sequence, transactions from the same account are processed in sequence order, and transactions must respect time-based limitations. For conflict resolutions, later transactions fail if the account lacks balance. If we have sequence gaps, transactions with these gaps in sequence numbers are rejected, and order book operations follow strict precedence rules. Some distributed assembly challenges: how do thousands of independent nodes create identical ledgers without central coordination? We have deterministic rules, identical transaction processing logic on all nodes, standardized fee calculations and ordering, and consistent handling of edge cases. Inside the consensus mechanism, validators propose and vote on ledger versions. Supermajority agreement is required for finalization, and dispute resolution through additional consensus rounds. We also have synchronization protocols where nodes share transaction pools and ledger proposals. Missing data is requested and retransmitted, and network partitions are detected and resolved. So in summary, the XRP Ledger represents a sophisticated solution to the challenges of distributed financial infrastructure, combining theoretical computer science principles with practical engineering solutions to create reliable, scalable, and trustworthy system for global value transfer. Thank you for watching.